Today we're going to be talking about horizontal and vertical translations. This is the very first part of our translations unit. I wanted to start this lesson by reminding you of what we talked about when we were reviewing quadratics. If you recall, the graph of y equals x squared looks like this. It's a parabola that's symmetric. And if you remember, when we talked about using vertex form to graph parabolas other than just this basic parabola. So for example, something like this was in vertex form. And we determined that the vertex of this function would be 1, 2. Remember, when we take this number, this h value out of the brackets, it is an h value of positive 1. So this vertex is at 1, 2. When you sketch that, 1, 2, it means your vertex is now up there. And then you could go ahead and sketch the rest of this graph. You'll notice the difference between y equals x squared and y equals x minus 1 squared plus 2 is that this graph moved over to the right by 1 and up by 2. Because the vertex moved over, this entire parabola shifted over 1 and up 2. This is essentially what we're going to be looking at when we talk about horizontal and vertical translations. If I asked you, for example, to consider this function, you could determine that the vertex is negative 5, 3, from what you know of vertex form. This graph would move 5 to the left and 3 up, and its vertex would be up there. So what these two numbers, h and k, are telling us is that our vertex is moving to the left and the right and up and down. So when we talk about this in general form, we can actually use this same logic in terms of functions moving left and right and up and down with any type of function. We can use it with a cubic function, with an absolute value function, any type of function. And how we represent that is using this form. So this is in function notation. And what this is saying is that our function, g of x, is related to the function f of x by moving it side to side and up and down. So the h value, just like we saw here, when it was 1, moved the graph over by 1. And the k value, which in this case was 2, moved the graph up 2. Those translations are the same for any type of function. So the h value denotes the horizontal movement, and the k value denotes the vertical movement. If you notice the h value, remember in vertex form, that this value always appeared to change signs. So the same thing is true in this function notation. When we have a negative or x minus a number, this is actually showing that the graph is going to move to the right. Here we had x plus 5, which gave us an h value of negative 5, and this moved to the left. A k value that's positive meant we moved up by 2, or in this case, up by 3. So if we look at a few examples here, we have explain in words how each graph compares with y equals x squared. So if we change this to y equals x squared minus 2, This means we're going to take x squared and we're going to move it down 2. Notice x squared is a term and the minus 2 is our constant. That's why this is our k value. If you compare that to b, so this is the k value. If you compare that to b, where the x minus 2 is all being squared, this is our h value. And that graph is going to move to the right by 2. Notice how it kind of looks like it should be going to the left 2 because it's minus 2. Remember, horizontal movements always look the opposite of what they actually are, because when we pull that out and determine the vertex, it would be positive 2. So it moves right 2. If we combine and have an h value and a k value, like in example C, we move to the right 2 and up 1. Now, like I said, these transformations can apply to any type of graph. So in example 2, we have the graph y equals the absolute value of x. Remember, that graph is drawn here in gray, and that graph has this V shape that starts at 0, 0, and goes 1, 1, 2, 2, 3, 3, and on the other side, negative 1, 1, negative 2, 2, negative 3, 3, etc. I can take that V-shaped absolute value graph and I can apply transformations to it. So in part A, I've got y equals the absolute value of x minus 1. Those absolute value bars act just like brackets. This is a horizontal movement with the graph moving to the right by 1. So all I did was I started with 0, 0 and moved it right 1. 1, 1, moved right 1. 2, 2, moved right 1. All of these points moved to the right by 1. For part B, the negative 5 is outside of the brackets. So this is the absolute value of x, take away 5. This is a vertical translation. So this graph is going down by 5. So you can take each of your points on y equals absolute value of x, the original graph, and move them down by 5. Every single point goes down 5 to get your new shape. And in part C, I have two transformations, left by 4 and down by 3. So take each point and move it left 4 and down 3. Same here, left 4 and down 3 to obtain your new graph. You always want to check that your new graph should be a similar shape to your old graph. When we start getting into stretches, sometimes it can look quite different, but in this case I am just taking my original function and moving it left or right, so it should have the same shape when I'm done. In example 3, I have this function. The function f of x is this shape here, drawn in black. If I take f of x, and notice here, it's just called f of x. I don't actually have an equation to represent this function, but we can still treat it the exact same way. If we take f of x and we add 3, this is inside the brackets. Remember, that's like an h value. We'll move it to the left by 3. So I took each point on the original graph and moved it left 3, left 3, left 3. For part B, I have a movement left 3 and down 1. So left 2 and down 1. So left by 2 and down 1. And if you graph all those points, you'll get your new function. You'll notice that I have a table here, and this is called mapping. So for some of you, it might be quite simple to do this visually, to move these points over. But for some of you, you might find it handy, and especially as we get into more complex transformations, to have a table. And what we are looking at in this table is we're starting with a point xy. So all of these values are the original points on the graph. I chose 4 of them. In the second column, what I've determined is what happens to x and what happens to y. So because I'm going left by 2, I'm taking my x values and subtracting 2. And because I'm going down 1, I take my y values and subtract 1. So if you look at each point, -5, -2, and you subtract 2, and then subtract 1 from y, you'll be left with your new point, which you can plot. Like I said, for this kind of transformation, it's pretty straightforward, but this mapping comes in handy as we get onto newer, more complex functions. Finally, in example 4, I've asked you to describe the translation that's been applied to f of x. So f of x, this function, is the starting function, and I want to know how we get to g of x. So all that I did was I looked at this point here and figured out what transformations I need to get it to move up here. And if you notice, we're going up by 2 and to the left by 5. So in words, up 2 and left 5, but I've asked you to write the equation. So I'm just going to change this. This should say g of x since we know the name of the graph. It is named g of x. And it is equal to f of x plus 5, because we're going left 5, plus 2, because we're moving up 2. There's practice questions listed at the bottom. Try them out and let me know if you have any questions.